All right. So the question we just got, and correct me if I'm wrong, is, so what makes expanding capacity impure? And first of all, let's make sure we have a good understanding about what that means. A pure function, it's more of like a mathematical term, but basically a function is something that, takes some arguments and produces some output. That's it. It doesn't affect anything else. If I'm a function that you give me two numbers and I return the sum, that's all I do. An impure function, or a function with a side effect, is a function that may or may not have some output, or method that may or may not have some output, but it alters something somewhere else in your code. It changes something somewhere else. Imagine I had a function that added two numbers together, and you give it two numbers, a and b, and it returns the sum of a and b. So you give me 1 and 2, I give you back 3. That's a pure function. But if you have that function, and it also goes and alters some global variable in the meantime, like, oh, return 3, but also go and change the value of this global variable to be 3 too, it's impure. It's changed something, that code inside the function changed something somewhere else. A function, if it's pure, is like nice and self-contained. It's not going to do anything extra. And there's not necessarily anything, there's not anything intrinsically wrong with impure functions. It's not a bad thing. But the motivation for keeping your first of all, if you're ever in a position where you're like, well, I just can't make it pure, you're wrong. You can. You can do anything in one way or the other. It's not, one's not more powerful than the other. But the benefits, so the benefit of an impure function is like the function's doing what you need it to do. And this will be an example I'll talk about briefly. And sometimes it helps with kind of like compartmentalizing, like the purpose of this function method is to do x, y, z, right? Like it's like that's what this chunk of code, it solves this problem. And sometimes doing it that way might have side effects. And that, there's value there. But the value in having a pure function, a function with no side effects, is it's easier to reason about. You're not going to miss side effects. Side effects can go missed. Oh, here's a function that does this and does that. But like, if you didn't notice the side effects within the code, that could be an issue. So pure functions are easier to reason about, easier to keep track of, control of. They have some nice mathematical properties that make them, you can prove things about them that we're not going to get into. And they're easier to test. Anything with side effects becomes a lot harder to test. So when they're pure, it tends to make your code, see, I don't want to say cleaner, because I don't want to give the sense that impure is necessarily bad, but there's a lot of niceness that makes it a little easier to work with your code when everything's a pure function. What were you going to say?
Actually, I can comment on that last thing. Like, having pure functions could just be, like, if you're trying to debug and just figure an output, you have less things to keep track of.
Absolutely.
And also, I was going to ask, so do you personally like try to avoid in-place algorithms?
Not necessarily. Really not necessarily. But yes, right?
You would.
But it really depends on the context. So what he's saying is, like, for example, you've got an algorithm, and when you say in place, it can mean different things in different contexts. But like, let's say it's a sorting algorithm. Here's an array, sort it. Should you sort the contents of that array? Or should you return a new array that's sorted, but you leave the original array unchanged? When you sort the array, when you modify the values of the arguments, that's a side effect. The output of the function is like, that's really the only thing that's supposed to like happen. So if that's kind of what you mean in this context of like in place.
Yeah.
So and there's a lot of Python functions, built-in functions that are in place, for better or worse. So yeah, I get an array. Do I modify that array that I got? Remember, I didn't really get an array. I get a reference to an array. So do I modify the contents of that array such that it's sorted? Or do I return a new array that's a sorted version of the contents of the array that I got, but I leave the original array unchanged? What do you do? It's not necessarily one, I don't want to say one's better than the other, but I feel like 9 times out of 10, I would do the not in place one. I would make a new array, and I would sort the new array and leave the original one alone. And I think the reason I would do that is, one, it's pure. But two, doing it that way, I have a choice. If I have a reference variable called the array I want to sort, I give that reference to that array to the sorting algorithm, and it modifies that array such that the reference variable referencing the array that was just modified by the function that sorted it. Do you follow what I say or not really? Imagine I'll use these markers as visuals. You have a reference variable to this marker, okay? And you want to change the state of this marker, right? It's called marker that I want to change the state of. That's the reference variable to this, okay? So there's a reference variable. Someone point to this. There. All of you are reference variables to this marker. And you're called marker I want to change 1, marker I want to change 2. You're just all reference variables. You give me the reference variable, and I go, okay, I'll change the state of it. I don't even need to return the value. You're all pointing at this marker. That marker is now the state of it's changed. But that had a side effect, because that function modified something. It wasn't anything that was like returned.
The original state. You can't go back, I guess.
Where if we do it such that, now you might say, but that's exactly what I wanted. I didn't care about the original state. I wanted it in its altered state.
Always just make that the return value.
Exactly. You don't have a choice in this example where like, well, what if you wanted the original one left alone? Well, you'd have to make a copy of it beforehand to be safe. But now you're kind of like working to account for the side effect, where what I would do is you give me a reference to the marker, I would make a copy of it, leave this one alone that you're all pointing to, modify the copy, and return the modified copy. Then if you're like, well, I don't really care about having the one in the original state, fine. Everyone point to this now. Problem solved. Or if you did, the point is now you have a choice. Someone in the room is thinking, yeah, but one used more space. You're absolutely right. And maybe for your particular reason, for your particular use, that really does matter. Fine. Fine. But in general, it's probably not going to matter. And don't worry about over-optimizing. Was that clear? So that's the whole point of side effect, pure and impure. But now to get to the specific example. At the beginning of this semester, actually before this semester started, all of my expand capacities were written a little different. All of my expand capacities were written such that they were all side effects. What they would do is, in fact, let me go to the GitHub page and I'll see if I can show you what it looked like 6 months ago. This is another cool thing about everything on GitHub, is you can actually go and see how things have changed over time. Source. Let's look at like array stack. Modified 2 months ago, perfect. Somehow I'm on array Q again, but that's fine. So here, the array Q, I meant to go look at array stack, but whatever. Oh wait, no, here we can do this. Here's the expand capacity. You can kind of ignore this. I just changed some. What? Why does it keep going? Is this? Oh, I see the issue. Array stack. Okay. There. Notice that the original expand capacity, not the original, but the expand capacity from a couple months ago, didn't, can you see this at the back, or is it pretty hard? I'll zoom in. So look at the push, and look at expand capacity. Expand capacity is not returning anything here. It's a void method. Because what it did is it updated the reference variable itself. It updated the reference variable stack, that field stack, that was just a reference variable to an array that was the container for the elements in the stack. It didn't return anything. But this method has a big side effect. It's not pure. Usually when you see a method that's void, chances are it's full of side effects. Just because it's not void doesn't mean it doesn't have side effects, but usually it's a good sign. The method doesn't take any arguments. All it does is it actually just creates a new array and then it updates the reference variable, the field stack. It didn't modify what it received. It didn't receive anything. That's not where the side effect is. It didn't return any value, but it altered, outside of that function, there exists a variable, a field, called stack that was modified. That's the side effect. But I went and I changed this a few months ago because I was like, you know, there's nothing wrong with this. It's a private method. You know, I can make the argument that this is a self-contained method where the logic of it is it just addresses the issue with the array such that we don't need to think about the array getting bigger. That's like the spirit of what it's going to do. So it's fine. But I've been making a big point from 161 and into 162 about having pure functions. And we can make this function pure. So I modified it such that it looks like how it does today. It doesn't modify the field. It just returns the new array. And then the calling method, the inQ, was where I said like stack equals the result of expand capacity. Okay? So you could then say like, but you just moved the side effect. And I'm like, true, but push is going to intrinsically have side effects by the nature of the data structure. It's already full of side effects. Might as well put the side effects with the side effects. That was my rationale. And I did the same thing with the array stack. Sorry, the array queue, where it returns the new queue. But it still does modify two other fields. It modifies that array queue's front field by setting it to 0, and it modifies its rear to be size. And again, you can say, well, that method really is supposed to be taking care of that such that we don't even need to pretend it exists. It's a private. Fine. But one, I kind of want this method to be pure. We can move the impureness to the inQ, which is already impure, full of side effects. And also, I made an effort to make this a pure function, and I didn't finish it, though. I only eliminated some of the impurity. I could have eliminated all of the impurity.
Do you think you'll change it to do that?
Yes. In fact, I was thinking about it this morning, and I didn't want to make a change right now, because I didn't want to change it in the middle of a semester. But what I did do is on my GitHub page, I created an issue, which is effectively a reminder to myself that says, make expand capacity less side effect-y. And I explain why. So 8 months from now, I'm going to go, what? Oh, that's, yeah, right, yeah. So there we go. I thought about it because I thought I had fun talking. But then I was conflicted because I thought it was a good opportunity to revisit side effects. And this is a good example of side effects. But pardon?
You still do what you did now.
Yeah. Did that answer your question?
Yes.
Okay, cool. I think that's a good question. At the end of the day, if your code is full of side effects, that's not bad. But you are going to miss out on a lot of value that you get from having pure functions. It's not bad. People could even argue that it's not necessarily better to have pure functions, but you won't get the benefit of having pure functions, that's for sure. Like when you have side effects, impure functions, think of your code as a bunch of functions and data, kind of like in boxes. Just whether it's function or data, whatever, just imagine like I've got a bunch of like boxes here. When your functions are pure, they just kind of like do their own thing, right? They're all nice contained. But as soon as they start to have side effects, they're going to start messing with other things elsewhere, and then you end up getting this like web, which is kind of hard to kind of keep track of.
Kind of like in computer science, we call functions like a little black box, and put something in and the option comes out. But I mean, if it was an impure function, you put something in it, then
You get something else,
then something else changed for some reason.
and that door opened. Exactly, yeah. Yeah, you want your functions to be like, throw something at me. Just pretend to throw something. Great, here you go. Throw something at me. Great, here you go. An impure one, throw something at me. The door opens. What? That's actually a good example. You don't, that's obviously, if you're left going like, why would that happen? Exactly. Cool. Hopefully that was a good refresher on side effects and whatnot. One of the big tricks to eliminate side effects is to eliminate states. And so raise your hand. Okay, you're done assignment 2. Raise your hand if you have kind of at least been working a little bit on assignment 3. All right. So I could have implemented assignment 2 and 3, the maze, such that the maze knew which cells were visited. There's nothing wrong with that, right? But then that gives the maze a state. And there's nothing wrong with that. But that means all the methods I have, whenever anything's stateful, it's hard to keep track of. And you're going to have side effects, because you're going to have a method that goes and updates some state of that thing. So I didn't want the maze to have a state. In fact, one of the earlier iterations of assignment 2 and 3, the maze did have states. And what was kind of nice about that is you could print out the maze at every state along the way. Because you know how now, when you're done, you can print out the maze with the solution. Before, when the maze had a state, and we could do it this way still, kind of. Before, when the maze had a state, you could print out each state at every iteration. And you can kind of like see it like solve the maze in real time, which was neat. But it created a lot of headaches for students, where students started getting bogged down by the states of their code, when there's always it's always good experience to deal with complex code, because you get a chance to explore and figure it out and learn. You're going to learn a lot by doing that. But I kind of really wanted you to focus on like, this is a stack, right? That was the point of the assignment. So I changed it so the code was cleaner, better for sure, and I eliminated the maze's states. And instead, we used some alternative data structure to keep track of the cells that were visited and whatnot, right? So the maze would have cells, and each cell could know if it was visited or not. But instead, we used different data structures to keep track of what was visited and whatnot. So whenever you're in a situation like, well, okay, I need a state, do you or could you use an alternative data structure to keep track of that for you? And if you eliminate states, that's a good thing. It's cleaner. Yeah?
Is that kind of thought also, if something has a state, especially if it has like so many different states, if you wanted to like reuse this thing like over again, you'd have to like kind of reset it to its original thing and then like,
Yep, absolutely. And I think in the original iteration of the assignment too, the cells knew if they were visited, the maze had cells, and the maze would also solve itself. The maze had a solve method built in. But the maze is just data, right? The maze doesn't need to know how to solve it. The maze is just a maze. Why would a maze need to solve itself? You can write a maze solver class that can solve a maze. But a maze is just data. And a maze solver is just functionality. A lot of hardcore object-oriented programmers would be like, well, that's the point of object-oriented programming. You take data and you take functionality, you put it together. And then a few years went by and then people were like, maybe object-oriented ain't great if you do it like that all the time. Just because you could doesn't mean you should. People are going to go like, yeah, maybe keep your data and functionality separate. They can go together. You can give a maze solver class, which is just a function, right? Solve. You can give that method data to work on. But the point is it's separate. And that's a good thing. It's not bad if it's not, but it's definitely nice if you can keep these things separate. All right, back to content. Actually, any last questions? I think this was good. This was really good to talk about. I mean, the last few lectures, we spent some time talking about like code aesthetics, for lack of a better term, which I think is a good exercise every once in a while. All right, bags. So this was the interface for a bag. We want to add something to a bag, remove something, check if anything is contained in there, count is empty size, and get an iterator, which we'll learn about later. Long story short, it provides a nice, consistent way of iterating over your data. Iterating, it's a linear collection. Start at one end, go to the next, go to the next, go to the next, and so on. And I mentioned this last time. With a stack and a queue, these things are very well defined. A bag, not so much. If you're saying, why do you have that contains there? I looked it up on Wikipedia. There was no contains, but I looked up stacks on Wikipedia, and there was a push and a pop. Well, yeah, because bag is more general. It can be whatever you want it to be. Why don't I have a method that sorts? Because I don't. I could, I guess. Didn't need it. But we could play this game forever. This isn't a well-defined structure. It's just some bag that we're defining right now. But that's just a basic bag. And you remember we talked about two other forms of a bag, a sorted bag and an indexed bag. They're both bags, but they're specialized versions of bags. One is, well, the data is always sorted. If I want to add something to that bag, it goes where it goes. It goes such that the data is still sorted. If it's an indexed bag and I add something, well, I can add it wherever the hell I want. I can specify the index I want to add it at, assuming it's valid. So we can have a sorted bag. And a sorted bag, you'll notice, only has 1, 2, 3, 4, 5 methods. But actually it doesn't. It has more. First and foremost, it has, equals, hash code, toString, right? But we didn't need to include those because we get those for free because it's an object. Everything's an object, and from the object class, we inherit some methods. So we don't need to specify them here. But I am actually, now there's a lot of stuff going on that top line of code. And we are going to break it down, don't get me wrong. Public interface sorted bag T extends comparable super T extends bag T. Holy moly. We'll get into it, don't worry. It'll actually make good sense. Well, it'll make some sense, but you might be plugging your nose and going, all right, it's the magic code. Whatever. We'll deal with that for now. But the thing I want you to notice right now is at the very end it says extends bag. And this is a keyword that says we're going to effectively inherit everything that a bag is, but add to it this stuff. So it's a specialized version of a bag. It's a bag with this stuff added to it. So this right here includes add, remove, contains, count, is empty, size, and iterator, but also has these. You can think by including the extends bag, I'm copying and pasting, copy, and I paste these in here without having to actually copy and paste them in. Now, you will notice, this is just a talking point. It's not actually overly important, but I will bring it up. You will notice that there actually is a repeat. The Boolean add t element. Boolean add t element. And we all know that the at override is not necessary. We don't need that. But why would I include a method that already exists here? And the only reason, this really is a design thing that I decided to do. I didn't need to include it. But because if you go and you actually look at these interface files, because they're interfaces, not classes, if you look at the interface file, what's not included on these images, right, on this code right here is all the Java docs that explain what each method does. The add for assorted bags Java doc needs to be more precise in saying like, well, it adds such that. So the only reason it's actually included is so I can write a Java doc that makes sense for this interface. But it's not functionally necessary, FYI. So a sorted bag is everything a bag is plus this. Now, a bag is generic, and sorted bag is generic too. Where do I talk about this? Okay, yeah, here I'm gonna read this because I've explained it pretty well, I think, and I'll just say it again. Notice despite wanting all the bag methods, they are not included. This is because sorted bag extends bag. The extends keyword means that the interface class will inherit all of the methods from the class being extended. I will warn you, it's usually pretty safe to use like inheritance in interfaces, but as soon as you start using inheritance in concrete classes, you end up, there ends up being issues that can arise. Just FYI. Just as a warning, this won't come up for the rest of the semester, but just if in the future you'll be like, I remember Dr. Hughes said. Yeah, I did say. Now, bag is being extended. Similarly, the type T extends comparable. I'm going to discuss this in more detail later. Okay, I guess I don't go into the details here, but what I will explain is, okay, look. It's generic, but this is a sorted bag. And the type, T, that we're going to have in our extended bag, in our sorted bag, right? This here. The type of the data that's going to be in our sorted bag must be orderable. Remember with a sorted bag, the type of the data determines its ordering? If it's integers, you order it based on numbers. If it's letters, alphabetical, right? The things that we want to put in a sorted bag must have some ordering to them, otherwise it doesn't make any sense. Like put this car part in the sorted bag, and you're going to like, how am I ordering these things? It has to have some defined ordering. So the T must extend comparable. And the comparable class, this is another form of inheritance, is if something extends comparable, that means it must be like sortable. It must have some defined ordering. So that's what this is saying. So yeah, it's generic, but there's a restriction on how generic it is. It's generic, but the thing must have some defined ordering. That's what that is. I'll go into more detail about this a little later in the semester. I don't know if it's in this topic or a future topic, but yeah. Any questions about that idea, though? Because if I said, here, I'm going to give you colored construction paper, and I want you to sort it, the first question you're going to ask is, how? That's what Java wants, too. If it was generic, I'd give it construction paper, and it's going to go, how the hell do I sort this? It needs to actually have some ordering defined for it, because it's the type of the data where the ordering is defined for. Questions about this? From the looks on people's faces, I'm gathering about half the people are like, yeah, cool, makes sense. And the other half of the people are like, I don't believe you. So which is it? Raise your hand if you believe me. Cool. So although not explicitly included, the methods from bag are still a part of what a sorted bag is because we extend it. A sorted bag cannot be implemented without implementing the methods from bag. So remember how like when you started to implement a stack, right? You said public class array stack implements stack. And immediately IntelliJ was like, you didn't implement the methods for stack. Remember how it would yell at you? Everything was red. And there were a couple of things to do it. I mean, the solution was just implement everything. But you could just tell IntelliJ to put in all these dummy methods to just shut it up. They would all like return false, return 0, return null, right? So they existed, but it didn't actually solve anything. With a sorted bag, if I went and I tried to implement a sorted bag by only implementing these methods, it would yell at me, saying I'm not done because I didn't implement everything from bag. I need to implement everything from bag and sorted bag. And if you don't believe me, you'll see. So now an index bag. Index bag maybe is simpler, at least to kind of wrap your head around in terms of what the interface looks like. Index bag will make use of inheritance. They're both bags. An index bag and a sorted bag are both bags. And some of the functionality of what we want the bag to do is going to be common between them, but some of them are different. As you can imagine, sorted bag, index bag, they have different things. So what do we want the index bag? Well, we've got add, and again here we've got the override, and really the only difference is we have to really the only reason I'm including the duplicate add is for the Java doc. But we've got an add that takes an index, a set that takes an index and an element, a get something at a specific index, remove something from a specific index, index of some specific element. You'll notice too, I have two adds. It's an indexed bag. This add makes sense. Specify an index and the thing you want to add at that index. Great. What do you think the other add should do, the add on line 4? Add to the end. It's like append, basically. But that add exists in the parent class. Parent class being bag, what it's inheriting from. But just like the sorted bag, the only reason I'm including it here in the interface is for the Java doc to say like, it's basically append. Because it's got such specific functionality that the interface should describe what it's going to do. But you'll also notice that there's a remove. And there was a remove in the regular bag. It returns a Boolean. You give it an element that you want to remove, and it returns a Boolean. But this remove is different. This remove, you give it an index, not an element, and it returns the element at that index. So it has the same name, but it's a different signature. It's got different functionality. You would use it differently. So even though it's got the same name, it is a different function. So one remove is like, remove such and such an element from the bag. This one is remove the element at index whatever from the bag. Different functionality. Any questions about any of these bags at this point? So we defined a bag. And then we define two specific types of a bag. They're both bags. They have some commonality, but they are unique. They're different enough that they'll have their own classes. Everyone's okay with this? All right. And I'll show you what I mean, right? Like if I go, yeah, oh yeah, download my insecure file. Just notepad. Like, oh, it's so small. But you'll see the add. The only reason it's there is because of the Java doc. Adds the specified element to the sorted bag such that the sorted bag remains sorted. If you go look at the regular bags, keep, download, yeah. Apparently opening a text file is too hard. Let's see. This will be my last try. All right, I'm guessing it's not opening for some funny reason. But if we were to look at that file, just the Java doc would be different. That's all. All right. So I talked about extends. I talked about inheritance. What's going on? It's really not more sophisticated than what you probably already gathered from what we talked about in that context. But I'll go into a little bit more details. Inheritance. It's a way to derive a class from an existing one. And I'm going to warn you. Inheritance, one needs to be careful using inheritance. Because we often try to do object-oriented programming in a way that mirrors reality, which sometimes becomes a bit of a nightmare code-wise. And the only way you get better at doing inheritance well is with experience. But one should always be very cautious with inheritance. So inheritance is a way to derive a class from an existing one. And this allows for the ability to inherit some functionality from the base class. So your vehicle, right? And like, oh, well, you know, we can categorize. And I think this need for we want to use inheritance because humans are so obsessed with categorizing things. Like, oh, we've got vehicles, and then a higher resolution view of that is like, well, we could have aircrafts and buses apparently, and then within those we can have more, and within those, you know, we want to categorize everything, right? Maybe resist that urge all the time. Resist that urge to do it all the time. Not all the time, never mind. So here's an example of what the inheritance structure looks like with our bag situation. No matter what, even though we never write extends object, we always inherit from the object class, whether you like it or not. That's where we get our toString equals hash code, get class. There's a bunch of functions, methods, that exist in the object class that we get for free because we inherit it. And we don't ever actually explicitly say extends object. We don't need to do that. But we wrote a bag. Now actually we only wrote the interface, which is usually pretty good. It's safer to do inheritance with interfaces. And then the bag, there were two specialized versions of bags, sorted bag and indexed bag. Oh, I've got a typographical issue there on that caption, an extra backtick. Indexed bag inherits from object and bag. Sorted bag, object, bag. But they're independent from one another. This hierarchical thinking extends in everyday life. However, one should be careful not to translate what makes sense from reality to code. All right, terminology. I'll just give you some terminology. Fortunately, it's fairly intuitive. The class that is being inherited from is called the superclass. Is often also called the parent class or the base class. Right? I think those are all relatively intuitive. And the class that is inheriting from the superclass is called the subclass or child class or derived class. I probably use parent and child to be, like, I probably use those words most commonly, but these are all normally used words. When considering the hierarchies, these terms are all relative. A sorted bag is a subclass of bag. A bag is a superclass of indexed bag. An object is also a superclass of bag, sorted bag, and indexed bag. Cool? Cool. Object. The object class, not to be confused with objects. The objects class is just a static class that has a bunch of static methods that are handy, like contains that equals that we were using, right? But the object class is always at the root of the hierarchy, whether you like it or not. And there's actually a lot of value that we get from this. If I know that every object must inherit from the object class, then I know every object I can call toString on, right? No matter what, I can call toString on it. Whether or not there's a good implementation of toString for any given class is irrelevant. But the point is that method exists. Equals. Whether or not it's a good equals for any specific class is irrelevant. The point is, no matter what class you give me, whether it overrides the object equal or not, I can call equals on any object. No matter what, I can always call it. It's safe to do so. There's a lot of power with that. It makes coding a little nicer, cleaner there. So every class in Java inherits from object. Although it does it automatically, we don't write extends object. Child classes inherit everything from their superclass. This means that all the methods from object are inherited for free. ToString equals hash code, there's more. However, they are typically overridden within the class's specific functionality if they are to be used. For example, inherited behavior of equal checks if the references are this exact same object. So the default equals, the equals we get for free from the object class is sameness. Literally, do I have references to the exact same object? But that's often, I mean, for your use, for your specific class, that might make perfect sense. But if we're thinking of a person class, should equality be defined based on sameness, or should it be defined based on like a student number, right? Can I have two copies of the same thing that can be determined, that can be considered equal? So we overrode the equals for whatever we wanted to define equality between objects. If we go and we look at, for example, there's a lot of these hierarchies out there in Java, but if we load up the Java standard library and we look at the collections aspect of the library, collections is where you're going to see things like lists, queues, sets. This is the actual class hierarchy, right? Purple means we have an actual class. Blue means we have an abstract class. I'll explain that in a moment. And an interface is an interface. An abstract class is basically between the two. There's some concrete methods in it and some basically incomplete methods that you actually have to implement. You can't actually make an instance of an abstract class. You can only make instances of concrete classes. So you have a bunch of interfaces that can inherit from one another, like a queue. Let's see if I can find a good example. We have collections and we have sets. And then a subset of a set could be a sorted set. And then under there we have a navigable set. So a navigable set is a sorted set, which is also a set, which is also a collection, which is also iterable, which is also an object. So we can play this game forever. Now, I'm not showing you this to be like, learn this. No, that's psychotic. In fact, there's going to be a lot of programmers, experienced programmers, that look at this and go like, Java, what were you doing? This is not clean. This isn't simple. And yeah, I see that. But it is what it is. Okay, abstract classes. Notice abstract class designation. Abstract class is one that is declared to be abstract with the keyword. So you would say like public abstract class. It declares may or may not include abstract methods, method signatures, just like the interface, no actual code, just like the signature of the method. When I say signature, I mean like, okay, it's return type and name and argument types. That's what the signature is. It can't be instantiated, but it can be subclassed, inherited from. It may include concrete methods that will be the same among. So it's kind of like a middle ground between an interface and an interface and a class. It's like, okay, well, I want to inherit from this class because I can have two different, like a sorted bag and an index bag, but some of the functionality is going to be the same. So I can make an abstract class where the code literally is the same. So I don't need to re-implement. Like you could do that. We're not gonna, but we could play that game. And if you were left scratching your head on, wait, abstract, pretend it doesn't exist, you're going to be fine. Okay, the abstract queue. So what do we have in here? Abstract queue. So I'm just giving you an example. The abstract queue class and its subclass priority queue. The abstract queue has several important concrete methods implemented within the abstract class. It also inherits a bunch from superclasses too. Within the abstract queue, there are implemented the add all, clear, element, remove. I'm not sure if this is supposed to be formatted like that. And the priority queue, which extends abstract queue, makes direct use of a few of these methods, but it also overrides and implements more concrete ones. This doesn't matter. Polymorphism. Now this matters. Polymorphism, let me pause. Are there any questions about abstract classes? Let me answer this question. Am I going to ask anything about abstract classes on the test? No. Okay, you're good. All right, polymorphism. This is important. And I think it's important to emphasize. So sometimes when students start learning this, they feel as if it's complex. And I think it's because you're misunderstanding what I'm saying. If you misunderstand what I'm saying, it does seem complex. But chances are, you would all predict exactly what would happen anyways. And this polymorphism is just the name that we give to what is happening in this situation. So it's not even really that the behavior can change depending on the type of the object. If I have a reference variable to a bag, okay, it's a bag. Remember how, oh man, we're out of time, never mind. We'll start here, this is perfect, we'll start here next time.